Hey everybody, so welcome. In this video, we are going to talk about the behavior of a logistic growth model. And you'll recall there's a recursive formula that we talked about in the previous video, and it was just the rate of growth, kind of our percentage of population to capacity grows as follows. So you have this R, which is your growth rate, and then you multiply by 1 minus Pn, well, if we're going up by 1, Pn, and then multiply that by uh, uh, P sub n. So this is the recursive formula for a logistic growth model. Now, you might ask the question, what is the explicit formula for this model? And it turns out that that's much harder than any of the other sequences that we've been looking at. And we'll talk a little bit about why and see some very interesting behavior for logistic growth. So one thing I want to do, though, before we get into that is take a look at how we could see uh, um, a logistic growth scenario kind of evolve, how we can see these populations evolve. And so here I have a particular case where R equals 2. So this is R, this is our growth rate. And we'll take a look and see what it says. Okay, so R equals 2 means that for this model, we have the following more explicit recursive formula, which is just 2 times 1 minus Pn times Pn. Okay, so this is the model for the example that we're looking at here. And I want to see how the population evolves um, as time goes on. So I gave a few different starting points in this graph. So here's one, here's one, here's one, here's one. So in other words, at time, well, I started at time 1, you could start at time 0. Um, we we kind of see how these populations evolve. So if we started, for example, one of the purple picture we start would be P sub 1 equals 0.95. And then if you put 0.95 into this relation, we can find P2. In other words, what is P2? It's 2 times 1 minus 0.95 times 0.95. And here you'll want to use a calculator. I've done this ahead of time, but you get something like 0.095 here. And what are you seeing here? You're seeing this huge drop from 0.95 all the way down to 0.095, close to 0.1 here. And then you can do it again to find P3. You use the same relation, the same recursive formula. So here you get 1 minus 0.095. And sorry, I should put this in parentheses, 0.095. Again, use a calculator and you'll see something like 0.1795. Oops, 195. Again, you kind of keep going. And again, you use your relation. It's the same relation you use each time. 95. And you're just putting the previous value into that recursive formula. And again, you don't want to do this by hand. It's good to go ahead and use a calculator here. I'm approximating here at each level. And then P5, again, you use your formula. And you see what you get. It gets around 0.4 here. Okay, so the purple, let's take a look at what the purple, now this is just with this particular starting value. So if you put in this particular starting value, you see this kind of evolution. So what am I doing here? This is the height is P1 here. When I go to 2, the height is P2. When I go to 3, the height is P3. When I go to 4, height P4. When I go to 5, height P5. And so that's what I'm graphing here in this sort of evolution of the sequence. It's just this plot, line plot graph. Now, I won't go through the computation for each of these other ones, but I also put in the zero 0.7 value and got this graph. I put in the zero 0.2 value and I got this graph. And I put in the zero 0.1 value and I got this graph. And you might see some kind of pattern here. And indeed, there is a pattern here. And that is that, in fact, if let's see what happens if I put in something that's not on this graph, but we'll plot it with, I guess we can use orange here. We'll plot it with orange and we'll put in P1 equals 0.5. Okay. So what's going to happen? Let's see. I will find out what P2 is by using the same recursion relation. It's 2 times 1 minus zero 0.5 times 0.5. And I'm going to go ahead and do this one by hand. This doesn't look too hard. 1 minus 0.5 is 0.5. And then 2 times 0.5 is 1. So this is 1 times 0.5. But 1 times anything is itself, so that you just get 0.5. So wait a minute. Now we can take a look. We started with P1 equaling 0.5. We get to P2, it's also 0.5. Well, we use the same recursion relation here to get from P2 to P3. In other words, we put 0.5 in here, but we just did that, and we'll get that P3 is also 0.5. P4 is also 0.5. In other words, we are at what's called a stable equilibrium. So we just kind of stay right where we are, nothing changes, and we're going to get a really simple line, constant line as our graph. So that's a stable population, meaning the population is not growing, it's not decreasing, it's just stable. Every step, it just stays the same. It's constant. But when we look at that, and then we look at the other cases, the purple, the green, the blue, the pink, it seems like those other cases are sort of getting closer to that particular equilibrium. And indeed, that is exactly what's happening. So here we say that 0.5 is a stable equilibrium. And the other different I don't know if I'm spelling equilibrium right, but that's stable equilibrium. And the other evolutions that we're seeing are all converging to that stable equilibrium. And so that's an interesting model of a population, is that you're getting closer and closer to sort of a fixed system. All right, so I'm not going to go through the details of each of these computations for the next few cases, but what I want to do now is I want to look at what happens if we were to change our growth rate. Remember, R is called the growth rate. So it really controls a lot of what's going on in a very interesting way. So in this case, R equaling 2, we have a system, some kind of island and some kind of population that converges to a stable population. What happens if we change R? Well, if I change R to something like 3.2, what ends up happening is I get a situation where my population starts out, it can kind of move around, but eventually it settles in to a pattern of just periodic up, down, up, down. In other words, there are sort of two places that look like there are equilibrium, like a point 0.8 here and a point 0.5 here. There are two kinds of populations, and you sort of bounce back and forth between them. And that's a very interesting case because your species is sort of growing in one generation and then shrinking because it's overgrown, so it shrinks back to another state, and then it grows again to another state. But that's the kind of behavior you witnessed in the logistic growth model when your growth rate is around 3.2. And you might think, well, that's interesting. And it is interesting. This is what we would call a periodic, maybe a two periodic system. Because why two? Well, there's two different kinds of values that you're bouncing between. If you go up a bit in the growth rate, r equaling 3.55, then all of a sudden you might notice the graph. Here I included a lot more time. You might kind of be able to chop out like a graph like that and see that that actually is sort of repeating itself over and over and over again. And so what's happening here is, well, let's see. We have 1, 2, 3, 4 sort of stable places. Maybe you don't call them stable, but they look like you're bouncing between these 4 different values. And indeed, this is what you would call 4 periodic, is that it sort of settles in after maybe an initial movement around, it will settle into a pattern where it just bounces between 4 different populations. That's very interesting too. If you increase R even more, say to R equaling 4, you get a very strange looking system. It doesn't seem, as you plot it out, to really be going anywhere. It seems to go all over the place. Maybe here you might think it's kind of starting to repeat, but if I plot it out even more, it starts going wacky again. So in R equaling 4, it turns out you don't have any periodic behavior. Here, what you would have is something which is maybe known as chaotic behavior. And in other words, it's very hard to predict what's happening. And that is very interesting because if you think about it, how simple is this? I mean, we just did a computation where we could easily say, you know, start here and just we'll go from there. We'll be able to figure out what happens next. So we have a very simple recursive formula, and yet the behavior becomes fairly chaotic just by changing the growth parameter up. So in fact, this is a model where chaos starts to take hold. And there's a whole notion of chaos and subject of mathematical chaos that has been really studied for several decades now. And this picture here is a logistic growth kind of diagram of of where the stable equilibria are. It's a very famous picture. There's this area down here, the x-axis is your growth rate. This is the value r. So when you're down here, if you start out sort of in this regime where I started, even lower really, I think I started at 2, but it would continue on like this. There's this one sort of equilibrium that you converge to. So we saw that in the first case where, okay, if you were at a certain value, you would be converging to that single equilibrium and your population would be stable. The next example, if you look back, was 3.2. It was right around here. And here, there are 2 values. One is a little bit above around 0.5 and the other is close to 0.8. And those 2 values, you sort of bounce back and forth between them once you settle in. And that's exactly what we saw here, right around 0.8 and zero 0.5. These were the values where we started to bounce back and forth. Once you get beyond 3.5, you start seeing 4 equilibrium. And that's what we saw in that next graph, is that the population sort of alternated and bounced between these 4 stable points. But then I gave you 4. What did I give? 4. I gave you 4. And you can see there's all kinds of stuff going on there. And it's very difficult to see, okay, well, where's the population going? I mean, it's shooting over to another place, another place. It doesn't look like there's any stable equilibrium, and indeed, chaotic behavior ensues. So if you're interested in this kind of thing, if you're heading towards biology or any other sort of system that might rely on a recursive relation, there are courses like chaos and dynamics and math that you could look at taking. All right.